Okay, so last time we did, we kind of finished up our whole like quaternion discussion and did LQR with quaternions. And as I mentioned last time, like from there, it's pretty easy to imagine doing like DDP, ILQR, and also collocation methods with that same set of tricks. So you should be good on that stuff now. So now you can do backflips and aerobatics and stuff, and that's super fun. Okay, so what we're gonna, and then the other thing we did at the end last time with our little extra time there was talk about, start talking about contact stuff, which is, one of the other, I feel like there's a few weird quirky things that show up a lot in robotics that aren't classical optimal control topics that like I kind of want to cover. One was that quaternion stuff. And this is kind of the other major thing that shows up a lot in robotics that isn't part of kind of the classical canon of optimal control, but that is important, I think. So we're going to do that stuff. So today we're going to kind of really flesh out that story a lot more. So the first thing we're going to talk about is contact modeling with kind of within the sort of hybrid systems framework, which is one of kind of the two main standard ways to think about this stuff in robotics. And for those who aren't necessarily robotics people, like our electrical engineer friends, this stuff does show up in other areas as well. This basically comes in whenever you have switching systems, right? So this is not, purely a robotics thing. Okay, so, and then we're going to take this stuff and try to apply it to start thinking about legged robotic systems. So in particular today, by the end of today, we're going to have a hopper hopping around, which is kind of fun. And that's kind of the easiest legged system there is to think about. So we're going to do that one. And then I think we'll probably have you do some slightly harder stuff on the homework. I think we'll get you to do like a little like compass gate, like two-legged walker on the homework and stuff. Okay, cool. Any questions about that? All right, here it goes. So we're going to start out today with, we're going to revisit question. It was a question on the first homework, this QP falling brick thing that I had you guys do, which was foreshadowing some stuff. So we're going to kind of go back to that and talk about that a little bit. So we're going to do the falling brick problem two ways. We're going to do it that way, and then I'm going to show you kind of this other viewpoint, which is kind of the hybrid one that we're going to talk about today more. And these are basically the two kind of ways of dealing with contact generally in robotic stuff. So let's think about a brick. So here's the ground, here's the brick. And let's say, you throw it with some velocity v naught, and it kind of falls and then hits the ground and then slides or something, right? So you can imagine, I don't know, a brick falling on ice, say. And so it's going to slide on top of the ice when it hits the ground. And we're going to leave out friction for now, but it's not hard to include that just to make this conversation, nicer and easier. So we're going to talk through the details of what was on that QP question on the first homework, where I just threw it at you and told you to make a QP solver. Now we're going to actually talk through the physics of that. So here's what a time stepping method looks like, which is kind of what was that QP thing was all about. And this is one of the standard ways of doing this stuff. That's actually the one that's in most of the robotic simulators. So here's the basic idea. So you're going to take, so in this case, right, this little brick, we're going to write down F equals MA for this guy. So MV dot, so MA, and you've got gravity, so minus mg. And then you've got a contact force, which we're going to write like this. J transpose, which is a Jacobian that I'll write in a sec, and then times lambda, which is going to be our contact force. And the fact that I'm writing it as a lambda is supposed to be, I don't know, a foreshadowing of things to come. It's going to end up being a Lagrange multiplier. So here we go. This is called the contact Jacobian. And this is called, this is going to be the contact force. And then I guess I should write these other guys down. So we've got G is going to be kind of the thing you would expect, 9.8, whatever down here if we're doing MKS units. And then the state is going to be sort of Q and V here, the position and velocity. So Q is 2D, V is 2D, right? The whole state is 4D. And then we've got, so this is the dynamics. Then we've got this other thing that's going to go along with this. It's a constraint that we're going to write down in terms of this function. That's the standard notation here is phi for this thing called the sign distance function. And I'll just write it down real quick for this problem. We can talk about it. So if I have Q, which has the X and Y components, this thing's actually our Jacobian J. This thing is called a signed distance function. So this thing, the sign distance function, you set this up such that it has to be greater than equal to 0. And what this is just saying here is that the brick's not allowed to go through the floor. So you say this function, which evaluates to 0 when you're in contact and is negative when you're through the floor, this thing has to be greater than equal to 0. So this whole thing that says sign phi greater than equal to 0, sign distance function greater than equal to 0, this is called an interpenetration constraint. Okay, so we set this up. We've got F equals ma and basically our interpenetration constraint. We want to smush these things together into an optimization problem. The first thing we have to do is discretize this in time. And we're going to use, for this particular problem, the standard thing is to use some kind of backward or implicit Euler, which we talked about back at the beginning, right? So we're going to go ahead and do that. So what that looks like now, if I basically go ahead and discretize the F equals ma equation, I'll get something that looks like this. So the V dot is going to become Vk plus 1 minus Vk over a time step h. So just a discrete, like discretized finite diff approximation of V dot. And then the right-hand side, we can pretty much leave alone here because these are all constants or whatever. And we're just going to put a time step on the lambda there, lambda k. So that's the dynamics. Then we also have the kinematics, i.e. integrating the position from the velocity. So that just looks like this. And because it's backward Euler, right, we use the future time value of v in there to integrate the position. So dynamics with the contact force in there on the right-hand side. Kinematics. Now we've got our sign distance function in this interpenetration constraint thing, and we enforce the constraint at the next time step. So the idea is I plug in where I am right now, qk, vk, and I'm solving this optimization problem for qk plus 1, vk plus 1, so the next state, and lambda k, and the contact force, subject to this constraint that's saying basically I'm not allowed to be through the floor at the next time step. So this guy greater than equal to 0. There's a few other things that show up in here. Let's see. So also the contact force has to be greater than equal to 0. So that's saying that, so we got can't go through the floor. Lambda positive says the normal force that the floor is exerting on the brick can only push. The floor is not allowed to pull on the brick, right? So that makes sense. And then the last one is this thing. So this is phi times lambda has to equal 0. And this one says that you can't have any force at a distance. That's saying you can only have lambda be non-zero. You can only have a non-zero force if phi is equal to 0, if you're actually in contact. And if phi is positive, if you're in the air, then lambda has to equal 0. So this is saying no force at a distance, which also makes intuitive physical sense, right? Okay, so I wrote all this down, this whole stack, right? So we got dynamics, kinematics, interpenetration constraint, only pushing, no pulling forces constraint. And then this last one, that's this no force at a distance constraint. Does this look like anything we've seen before? This is a set of KKT conditions, right? This is basically a QP in disguise. I basically, from kind of physics, I wrote down these conditions, and then if I kind of look at these carefully, I'll realize that these are KKT conditions for an inequality constrained QP. And this is what was on the first homework, right? I basically just gave you the QP though. So this is kind of how you get there. So here's the QP that gives you those conditions, right? So it looks like min over VK plus 1, 1/2. And what I'm doing to get this, I'm basically pre-multiplying that whole first equation by VK plus 1 transpose from the left, such that its gradient with respect to VK plus 1 gives me the first line that I wrote down before. So this subject to this is the interpenetration constraint rewritten sort of, so it's just in terms of VK plus 1. You can also write this in terms of QK plus 1, and it'll be a little bigger with more conditions. This is actually the standard thing to do, is to just write it in terms of the velocities, and then after you solve this smaller QP, plug it back in to get the positions. So does everyone see how that works? I basically pre-multiply on the left of the first line with VK plus 1 transpose to get the objective function, such that that objective function's gradient with respect to VK plus 1 gives me the first line of the physics. And then this constraint is really just the phi QK plus 1 constraint, where I've evaluated QK plus 1 from the kinematics up here. QK plus 1 equals QK plus HVK plus 1, right? And then if I take this setup right here and write down the KKT conditions for this problem, when I introduce a Lagrange multiplier, I'll get that whole set of conditions up there, basically. Kind of slick. Okay, so let's talk about this for a sec. So this is, like I said, a very standard way to simulate dynamics. There's some weird quirks of this. One is, interesting thing is that when you solve this thing, you never actually resolve the exact impact time. Like you get the contact forces, but you don't know, like if you're imagining this brick touching down and hitting the floor, all you know is for which time step it hits the ground. You don't actually have any clue, nor does this like tell you or resolve where in that time step it actually hits the ground. So you don't get impact times, which may or may not, you may not or may not care. And it turns out in a lot of cases, we just don't care.
Can you not infer impact times from velocity and
you can try, but this actually makes it kind of hard to do that. What this is kind of doing is smearing out. So one way to think about this, you're kind of like zero order holding the contact force here. So that lambda k is actually a contact impulse. Sort of, it's the integral of the contact force over a full time step. And that's kind of smearing out the impact event over the time step. And so like, I don't think there's a super straightforward way to actually figure it out. It's actually like, and in this case, you probably could, because it's really simple, but in general, for like a big robot, it's got super nonlinear dynamics. It would be very non-trivial to actually try to do that calculation, just because the way this kind of inherently smears out all those contact things over a time step. Yeah. Okay. Let's see, what else? Here, obviously, the contact forces are explicitly computed. You get them in those lambdas. So that's often useful in robotics applications. Let's see. One other thing here, so when we set this up, right, I did this backward Euler discretization to get all this stuff. It turns out these so-called time stepping methods or contact implicit methods, they don't really generalize to higher order integration methods like RK4, say. You're kind of stuck with like Euler-ish, maybe midpoint-ish, like first or second order integration with these guys. Yeah, which has the kind of sometimes unfortunate side effect of needing to take pretty small time steps to get reasonable simulation accuracy. So this is often why if you ever use like Mujoko or Bullet, mostly is Bullet does pretty much exactly this. So PyBullet, Dart, they all do this. You often have to take like kilohertz or even a couple of kilohertz time steps in those simulators to have them not barf at you. And that's kind of because of this. They're basically doing Euler. And as a result, the integration accuracy is not great and you need really tiny time steps. What else is there to say about this? Yeah, basically this is I would say pretty much the standard setup. This is a very simplified, kind of this. It gets a lot more complicated when you do bigger robots, but this is the core idea, and this is sort of the standard thing, I would say. So, for example, probably the most popular one would be like PyBullet. PyBullet does exactly this. Dart does this. What else? Gazebo. And then also Mujoko does a kind of hacky, smooth approximation of this. So it's also kind of vaguely in this category, I would say. Okay, so any questions about this? Yeah.
Why is it that it can't handle
So it's pretty much in, if you, basically try it. So I have the continuous ODE there, and then I like discretized it to write down this QP. I use backward Euler here. You kind of can do it, but it gets really weird and messy and not fun. Like one way to think about it is like inherently what I'm doing when I do like an RK method is approximating the dynamics over a time step with some higher order spline, right? Like Euler, I'm basically like zero order holding or like using a linear interpolation between the two time steps. And here, like I only need to get a single lambda, and I can easily write down this, don't go through the floor kind of condition. There's a few ways to think about this. One is that like these dynamics are inherently non-smooth, right? And these impact events are doing discontinuous things. So like in some sense, approximating the trajectory over a time step using a smooth high order spline is a bad approximation when you hit one of these discontinuities, right? Like trying to fit that cubic spline from RK4, say, to like this giant impact event doesn't work very well. So that's like one way to think about it. You can kind of force the issue and try to do it. And I've kind of done some of this. What you end up having to do is actually introduce more Lagrange multipliers and more impact conditions. Because not only now are you thinking about not going through the floor at the QK+1, but now here it's a linear interpolant, right? So, okay, if you write down don't go through the floor, it kind of works out. If you have a cubic spline that can wiggle in the middle, if I say don't go through the floor at the endpoint, it still could wiggle underneath the floor somewhere in the middle of the time step, right? So you have to introduce like now more don't go through the floor type conditions, and it gets harder. You have to have more Lagrange multipliers. It just gets really messy. And it turns out it's not a big win because at the end of the day, the smooth spline is not a good approximation for the discontinuous trajectory. So that was a long-winded answer. Hopefully that, yeah.
Because it's specified and it's lambda k and that 2k plus 1, does that possibly?
So it turns out this tends to do the opposite. It tends to introduce artificial damping. So if you remember in the very beginning class, we did like We did Euler and showed that that had this bad blow up behavior on like the pendulum. Then we did implicit or backward Euler and showed that that had this like artificial damping effect. This is implicit or backward Euler here. So this tends to do artificial damping for what it's worth, rather than the opposite effect. So yeah, I mean, in general, yeah, it doesn't have great accuracy in it and not great, kind of energy behavior and stuff like that. But one of the reasons to choose the backward Euler here is exactly for these kind of stability properties. The other reason is that it naturally lets you look at you're evaluating everything at QK plus 1, which is how you also have to evaluate the interpenetration constraint. So it kind of naturally fits into a backward Euler setup here. Yeah.
Can you give an example of when you would need the exact impact time and not just the time step?
I mean, I've never cared in anything I've ever done. So yeah, I mean, I would say like, I don't think many people in robotics care because this is the standard simulation setup in robotics. And like, if I'm running this, like say in PyBullet, it runs this at like a kilohertz, say. So within a millisecond of when the impact happened, right? And if you care more than that, like, I don't know, you're probably doing something weird. Yeah, I don't know. Does that, I can imagine someone might care, but I've never had to care ever. So I would say there's probably some applications, but I don't know of any off the top of my head. Yeah.
How easy is it to like, or is it not possible to make this like an elastic collision so like the brick bounces?
Yeah,
And,
you
like,
can, it's possible, but not great in this setup. It's very easy in the other version, which we're going to talk about next. And we'll actually do it in a sec. We're going to do a bouncing ball. So you can do it in this framework, but it's kind of kludgy and not very natural. This naturally does perfectly inelastic conditions. It's kind of what comes out of this. And it's kind of easy to see why. Basically, if you look at the thing we're minimizing up top, we're basically minimizing kinetic energy subject to not going through the floor. So that like naturally produces inelastic things, right? Like if you had bouncing, you would not be minimizing that V squared term at the front, right? Yeah. Cool. Anybody else? Okay, onward. Oh yeah, okay, next fun question. So this is like the dynamics, right? And you can imagine like if I want to solve a trad problem to make my robot walk or whatever, these are the dynamics constraints now for my like before I would have like, I don't know, my Acrobot or something, and I'd have some nice algebraic conditions from like taking the ODs and applying RK4. Now my dynamics constraints are this whole set of KKT conditions. In principle, I can do that. But does anyone have any thoughts on why that might not work super well? Nope. There's one line in there that's bad for doing optimization. Yeah.
Is it the last one, the complementary selections?
Yeah, it's the last one. So everything else is kind of fine, right? Like the first line's fine. That's normal dynamics that we do all the time. Second line's fine. The next two are totally fine. They're linear inequalities. That last one, if you actually plot that out and look at it and think about it a little bit, we'll plot this. Like if I imagine having like a phi axis and a lambda axis, phi versus lambda kind of thing, what is the set that satisfies that condition in this plane? Like, so it's actually basically the y-axis and the x-axis, right? Are all the places where that's true. And this is like a super nasty, like, I don't know, it views it as like a set. It has no interior. At the origin, it does super weird stuff, right? So it turns out, in particular at the origin, it's non-differentiable. And then it's sort of, yeah, it's just bad from like a gradient-based optimization perspective.
Add like a small perturbation and get the two curves.
You can do that.
What is that bad?
That's sort of not the worst idea. What's that?
What do you mean?
So what do you do mathematically to get that to happen?
So you add like, instead of equals 0, you do like plus epsilon.
Yeah,
Like,
yeah.
really
So what is
small,
that?
And then you'll have to add another constraint. Well, I guess lambda's already working.
Yeah. So what is? Do you know what that is though? If you stick a slack on the right,
where I don't know what it's. I mean,
it's
you
literally what primal dual interior form methods.
Yeah.
do.
Oh yeah.
Yeah. So what you're
And then
doing
you
there
can
is
make- you can
essentially.
start with a larger and make it smaller and smaller and smaller.
Yeah. That's exactly. So that trick of relaxing the complementarity condition is what interior point methods do.
Yeah.
And it does, I mean, obviously it can work, it works in that context, right? So yeah, you can do things like this and they can work. It's very hard to make them work and you have to be very careful about how you do it. And this is like pretty much like researchy state-of-the-art stuff. Okay, so yeah. So this stuff is, you can do it. People have done stuff like this. We've done stuff like this. A handful of labs have done stuff like this to do what's called contact implicit trajectory optimization. Aaron Johnson's lab here has also done some of this stuff in the last few years, but it's super gnarly. And basically standard optimization solvers like we've used, like IPOps, just can't do this very well. So this is not a very common way to go. Common for simulation, but not common for like optimal control. Okay. Any other questions about that? Cool. So on to the next thing. So this is like kind of one of the two ways. The other way, which we haven't talked about yet, is this so-called hybrid approach or hybrid method. It's called hybrid in control. It's sometimes called event-driven simulation in simulators that work like this. And this is the more common approach in robotics in most control applications. And the idea here is most of the time, the dynamics are smooth. That's an assumption we make, or if we would like that to be the case. If that's the case, like this stuff kind of works pretty well. So we say we have some smooth dynamics, f of x, like the usual thing. And in the case of the brick, this is going to be, like this stuff, right? The flight phase dynamics look like this. And this is called a smooth vector field or smooth dynamics, whatever. And then what we're basically going to do is we're going to simulate these smooth dynamics using like RK4, pick your favorite integrator. And while we simulate it at each time step, we're going to check what's called a guard function. In our case, it's the same sign distance function. So we're going to check this guy. And in this context, called a guard. So we check this as we integrate the ODE. And then if this guard condition is violated, basically if we take a step and we go through the floor, what you do in practice is backtrack until you hit the exact phi equals 0 condition. So here you're resolving the exact impact time, basically, to whatever tolerance you care about. And then once you've done that and you've gotten exactly to the impact time, you execute this other function that's called the jump map. And that's sort of a function that captures whatever instantaneous, discrete, discontinuous thing is happening, right? So here we'll call this like x prime equals g of x. And in our case, in this impact case with the falling brick, this is going to look like the following. So we're going to not change the position at all, right? When it hits the ground, the position is not changing. What is changing instantaneously during this impact? So specifically the vertical component, right? If it's smooth, like ice that it's hitting, also the x component doesn't change either, right? So we leave everything else alone, but we zero out the vertical component of the velocity. This is, by the way, if I zero it out, it's a perfectly inelastic collision, which is what we had in the QP version. You can also easily add what's called a coefficient of restitution here, right? Where you flip the sign, multiply it by some constant less than 1 and get it to bounce. So this is how you would do bouncing. And we'll do that in a sec. So this function is called the jump map. And yeah, what we're actually doing in here, right, is And that would be perfectly an elastic collision, right? Okay, so that's kind of the recipe. So you have your smooth dynamics, your guard function, and your jump map. You basically stick these things together, and the like sort of simulation loop would look something like this, like in pseudocode. You basically do something like, you know, some kind of while loop while t less than, say, t final. If you're not violating your guard condition here, then you just do your usual thing. You integrate your ODE. And you can use any integrator you want for this. So like RK4 is fine. Then basically, you know, like else, you know, say you are hitting your guard condition. Now you're going to execute the jump map. And that's kind of it. And in general here, in this, you know, usually, right, you're never going to hit this perfectly with your integrator. So you're going to generally always step a little bit past it, right? And you'll detect that you've gone through. And like officially, you should backtrack and do sort of a line search type thing to find the exact instant to within whatever tolerance you care about. We're not going to do that today because it's, you know, it's you can figure that out. It's not that bad. So guard function detects impacts. And then the jump map simulates whatever your non-smooth thing is. Okay. Any questions about that? Yeah.
Does this have issues with sliding? It seems like while the guard function is triggered, we ignore dynamics and just preserve the velocity according to jump map.
So what do you think would be bad here, I guess?
For example, I mean, in this case, it's fine to frictionless, but if
Yeah.
you have friction, our jump map just says preserve x velocity, whereas if we have friction, we have to be changing x velocity.
Yep. So basically, this story gets a lot more complicated in general. In this particular setting, like you would actually end up being, so sliding versus sticking are two separate modes. So yeah, Coulomb friction is also discontinuous, right? You have to have, you'll have a bunch of modes and you'll have jump maps between every pair of modes. So this is getting at the whole, this other thing to talk about, whereas this hybrid setup, one of the major disadvantage of this is that it has this kind of combinatorial explosion in the modes. So you basically have to define a ton of modes to cover every possible sort of switching scenario, and then jump maps for all of those pairs of modes that can transition between each other, and it can very quickly blow up on you. So this stuff is really useful and really common in legged locomotion, where you can imagine for like a biped, it's like left, right, both, none. There's like 4 modes, you know, essentially. For a quadruped, there's a lot more, right? You can have all the possible combinations of feet on or off the ground, all of them, none of them, blah, blah, blah. Exactly. And now you've got also on top of that sliding and sticking for all of those. So just counting those up, it's a big number. It's like, you know, I don't know what it is. I haven't added it up, but it's like probably order 100 for just a quadruped, right? If you want to consider stick slip friction as well. So that gets nasty basically pretty quickly. Anybody else on this stuff? Okay, so like kind of summarize the quirks here, or whatever the pros cons of this stuff. First, these do resolve the precise impact time, unlike the other stuff. What about contact forces? So these things do not give you the contact forces explicitly. You can calculate them later by doing some kinematics-y stuff, but they don't come out of this for free. What else? Pro here is you can use, high order integrators here because it's just, during the smooth part, it's just an ODE. You can use whatever you want. And then this is probably the standard thing in optimal control and robotics. So widely used for trajectory optimization and MPC kind of stuff. And this is basically all the cool robot demos you've seen on Lego robots, like all the Boston Dynamics stuff, all the MIT Cheetah stuff, they're basically all doing this kind of stuff. And the kind of the key reason why this works well for TrajOpt, assuming you can, manage the number of modes and it doesn't explode on you. Okay, so the reason this is kind of attractive for TrajOpt is that basically if we know or basically assume or pre-specify the impact times, then we can basically like not worry about them in the optimization problem. They end up being like constraints that we pre-specify for like left foot's in contact at these time steps, right foot's in contact with at these time steps. You kind of throw them in there as constraints. And then the solver just figures it out and it looks pretty much like a standard trajectory optimization problem at that point. It basically just ends up being an extra set of constraints on like which foot is in contact at which time steps that you add to the TrajOpt problem. Otherwise, it's standard. So yeah, basically, if you do that, you don't need the guard functions, right? You also don't need all the complementarity stuff. So you just need these guys, and these guys are differentiable. So like one way to think about this is if you assume the touchdown and liftoff times for the feet and bake them in to the problem statement that you hand the solver, like you're really only optimizing then over the smooth arcs between, the impacts. And that's nice and smooth, and that's all differentiable, and life is good, right? Okay, let's see. Should we do some, I think this is a good time to do some code stuff. Oh no, definitely not. Joe Payne, I'm not saying that. Sorry. Zoom joke. Okay, where's the code? Here's the code. So the first thing we'll do is so this is actually straight out of the homework 1 solutions. This is just the QP stuff that you guys already did. So we'll just run this real quick. I think I'm running exactly what was in the homework. So it's 1 meter off the ground, 1 meter per second initial velocity, throw the brick, solve the QP at each time step. And you get this, like, this is showing you the X and Y components, right? So ballistic kind of trajectory hits the ground, slides. And then this is the velocity. So negative, 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 discontinuous jump in the velocity at the impact time, right? Cool. So you guys, everyone's just done this before. So we all know that. So let's go look at the hybrid version now. So here's the dynamics, which is just, F equals ma. Actually, and it's just gravity, right? There's no impact force stuff in this setup, right? We're going to use our K4 on that. The guard function is just returning the height. So when this thing crosses 0, that's when I have an impact. The jump map is going, so right now I'm going to 0 out, but we'll do bouncing next. So I'm going to 0 out the vertical velocity component, right? The last component of the state, just like we said before. Same initial conditions. We're going to go ahead and simulate this like we just wrote. Same rate, 100 Hertz, same exact parameters as we did in the QP. And you can see exactly what we're doing. So we're going to, time step through RK4. And then if we hit the guard, we're going to do the jump map. Normally, like I said, you would interpolate this back to, this is just detecting a crossing, and I'm just going to be lazy and do the jump map. If you were being legit about this, you would do a backtracking kind of thing after you crossed to get to the exact 0 crossing time. But we're not going to bother with that right now. Okay, and then I plot everything. So positions, velocities, and this exactly matches what we got in the QP, sort of unsurprisingly, right? So you can do it with both methods, and they kind of, in this very simple problem, they look pretty similar. And it kind of, you can pick either one. As we talked about a second ago, this setup, it's a lot easier to do stuff like bouncing or kind of elastic collision. So if I say set this to 0.9 now, what I'm doing here is taking this vertical velocity component, and instead of zeroing it out, which would be perfectly inelastic, I'm going to flip the sign on it. So I'm going to go from negative to positive, and I'm going to multiply it by this gamma, which in the parlance is called a coefficient of restitution. This is basically saying I'm taking out a little bit of energy, taking out like 10% of the energy kind of thing every time I hit, right? So this is going to get you kind of the behavior of bouncing a little lower, right, every time. So let's run this version. Oops. Okay. Blah, blah, blah. So you go bouncing ball. Interestingly, this is not without its quirks. Has anyone heard of Zeno's phenomena? Okay, so if I set this like, I can make this happen by setting this kind of low. Let's see what happens. This is coding on the fly, can get sketchy. It's not going to happen here. So one of the things that can happen here is, when does this, if I do this, when does the ball actually come to rest? Never, right? It, in theory, bounces, like the bounces get smaller and smaller, and they actually get higher and higher frequency, and they never actually get to 0. It's called a Zeno's phenomenon, and it becomes a problem with these methods sometimes. And you'll find in a lot of the control work on this kind of stuff, you have to make assumptions about this. You have to basically say, I'm assuming that we don't have Zeno phenomena and like a few other things. This can get weird. Anyway, okay. Any questions?
Kind of cancel itself out with the expression persistent.
So what'll end up happening is basically the bounce frequency is going to get, go up and up and up as the bounces get smaller. And you'll basically like, if you're using a good like variable step Runge-Kutta method, like you would get in like differential equations.jl or RK45 or something, the integrator is going to have to take tinier and tinier and tinier steps, right? If you do what we're doing here and you're just being dumb and using a fixed step integrator, you're going to actually get aliasing and stuff like this. Basically, you're not sampling fast enough to capture all those switches. And so it eventually like kind of just does weird, gross things. Yeah. Anybody else? Yeah.
This is more of a general question, but is there ever a situation where you would want to put a constraint on the contact force?
Yeah, absolutely. Yeah.
Then could you not use this method?
So you would have to basically bolt that on separately and write some more math to calculate those explicitly and then do something with them. But yeah, you're totally right. Like, I don't know, examples, you could like say, I don't want to break my robot. So like, I don't want to exert like gigantic forces, contact forces, or break whatever I'm manipulating, right? Like there's definitely lots of instances where you might want to do that. And so yeah, in that situation, the contact implicit stuff we talked about before, where those lambdas are explicitly in the problem, I can put whatever constraints I want on them, and it's kind of easy and natural, right? Here, you'd have to actually go and compute those some other way and add constraints on them that way, which you can do, but it's extra work. Okay, anybody else on this stuff? Okay, onward. Where did step go? Okay, cool. Tablet, please work. Hooray. So now we're going to go ahead and do the trajectory optimization thing using this hybrid setup. And we're going to do this on the simplest legged robot there is, which is kind of the monopod hopper. Has anyone heard of a Raybert hopper? Maybe kind of. This is like a dumbed down version of this, is like a dumbed down 2D Raybert hopper. Okay, so here we go. One-legged hopper. Here's the cartoon. Got a ground. You've got a body with we'll call it M sub B. We've got a foot, M sub F. We've got a prismatic joint connecting them together. And we can exert a force here, F, through that prismatic joint. And then we're also going to assume that you can exert a torque to swing the leg around. So you've got the F and you've got a tau up here. And that's basically what the Rayburn hopper looks like, except the Rayburn hopper's in 3D. So this is kind of a simplified version. The state for this is going to have a body position, which is 2D, and a foot position, which is 2D, and then a body velocity and foot velocity. So this whole state vector is 8-dimensional. And then we have 2 control inputs: the force in the prismatic joint between the body and the foot, and then the torque that I can exert sort of between the body and the foot also. So that's 2D. And what we're going to do this hybrid thing is define 2 different smooth dynamics models. Basically, we're going to end up defining a smooth dynamics model for the stance phase, where we assume the foot is pinned to the ground. And we're going to define another smooth dynamics model for the flight phase, where we assume that the robot's in the air, not touching the ground. This is kind of a standard thing to do in these hybrid methods. Okay, so if I write both of those down, we're going to call the first one F1. And this is going to be our stance. So, and effectively what you're really doing here is sticking a pin joint between the foot and the ground. And again, yeah, like I'm also here, I'm assuming no slip, right? So that's something, if you were trying to be legit about this and not have the robot face plant, you would then want to add some extra conditions on the tangential force at the foot to make sure you're not violating the friction cone conditions. And then we'd have our flight phase dynamics, which are the ones we already kind of wrote down. So cool. Okay, so we got those dynamics. We then need our jump maps. And in this case, we only really need one. So we're going to write down here, we'll call it G21 to mean that we're transitioning from mode 2, aka flight phase, to mode 1, aka stance phase. And that transition is an impact, right? And we're going to do the exact same thing we already did for the falling brick. We're going to write down an inelastic collision condition. So we'll have body, foot position. We're not changing the body velocity, right? The bodies can keep moving. We're going to zero out the foot velocity. And here we're actually going to zero out the foot velocity both in the vertical and tangential directions, where we're going to assume sticking contact. Okay, and then the reason kind of we don't need another one is the liftoff transition going the other way is just the identity. So when you lift off, you're not actually, there's no discontinuous stuff. So that's easy. And then the game here is, it's actually really simple once you have all this machinery. To turn this into a trajectory optimization problem, what we're going to do, and again, it's easy for a simple robot like this, where there's only a couple modes. I'm just going to alternate sets of time steps. So like, I'll write this down. So assign modes to alternating groups of knot points. By enforcing kind of the right constraints. And here's what that would look like in my kind of pseudocode, right? So let's say for k equals 1 to, we'll call it n1 for like mode 1, we're going to do our discrete dynamics. We'll say we'll start in a stance phase. So we'll start with, F1. And then at the end of, and also in here, we're going to enforce a constraint that the foot has to be on the floor during the stance phase to make this work. So we'll have also this constraint for all those knot points. Then we'll have a flight phase. So we'll say the next set of knot points. So k equals n1 plus 1 to n2. So this would be like, then we're going to just have our flight phase dynamics. And here we'd have to have this guy would have to be positive, right? And then at the next set of knot points, we're going to have a impact event. So we'd have something like x at that n2 time step is going to go through the jump map. And then we'd set this guy equal to 0 again. And then we basically repeat this. Now we'd have a new stance phase and blah, blah, blah. And we can kind of keep alternating just groups of knot points. And then, we'll have a nice standard trajectory optimization problem that we can solve with whatever method you want. You could do this with constrained DDP, do this with Dirk-Hall, kind of whatever you like. Question here is, so I'm putting these constraints in. Does this mean that I have to pre-specify the exact times of the touchdown and liftoff of the robot? That's exactly what I was just gonna get at. Yeah, basically, so while this seems very restrictive, in the case of a hopper, it's not at all actually, because I can do the free final time thing where I make the h's for each time step variable. So I can let the solver stretch out and shrink the actual times between these mode transitions and generate kind of more interesting things. What I can't do though is if I have, say, a quadruped where I can have like walk, trot, gallop, kind of different gaits, the thing that you are pre-specifying here is basically the gait. So if I do this, I can make the exact timing vary, but I can't change the ordering of the feet, touchdown, lift off. So if I start with like a gallop kind of gait, that's what I'm going to get. Yeah.
Could you do a very, I guess it's a very common point that, but try every combination of contact mode switches and see which has the best.
Yeah. So you just nailed it. Like that is, so that idea is basically what this TAMP stuff does. I mentioned at the beginning of the lecture. You can absolutely do like basically discrete search over these mode variables. Like these modes are really like discrete integer variables, basically, right? So there is absolutely a version of this where you can set it up as a mixed integer optimization problem where you have like a set of discrete variables and a set of continuous variables, and you can try to flip around, try various combos of discrete variables, modes, and there's smarter ways to do that than just brute force. The smart way to do it is with branch and bound kind of techniques, if you know what those are. Basically, you can kind of do tree search over the discrete variables. And so for each set of discrete variables, you're solving a continuous trajot problem, right? And there's kind of intelligent ways of like pruning that search tree where you can say, oh, this branch is going to have higher cost than this branch. So I'm going to just cut off the rest of that section of the tree and focus over here. There's smart ways of doing that.
Is it similar to alphabetical?
I don't know. I don't know what that is.
Similar to what you just described.
Okay, yeah. So in like this mixed integer optimization land, there's this branch and bound technique, which is very standard. That's basically intelligent tree search. Cool. Anybody else? Okay, cool. In that case, we will do fun things again. Okay, here's the code. So we're going to use IP-opt and do this with like a colocation style setup. You can also do it with DDP type methods as long as you have a way of handling constraints in your DDP method. So like our Altro solver in my lab can do this, like we showed before. This is just a bunch of problem setup stuff, states, controls, time, 10 hertz. This is something, I'm basically, what I'm going to do here is assign a mode switch every 5 knot points. You're going to have 5 knot points stance phase, 5 knot points flight phase, vice versa, just alternating. And the rest of this is just me sort of calculating random things that are useful. I'm basically like figuring out here which indices are going to be stance and flight phase and that kind of stuff ahead of time. Okay, hopper dynamics, here we go. So we're going to make the body, mass 5, the foot mass 1. And then the prismatic joint, we're going to put inequalities in there for the length of the prismatic joint as well. So it's got a minimum distance of like 0.5 meter, maximum distance of 1.5 meters for the prismatic joint. Flight phase dynamics. So this is just F equals MA, and then like J theta double dot equals tau kind of stuff. I guess the weird thing here is this B matrix, which is what this is really doing is mapping the force and torque into the sort of like accelerations for the body and the foot masses. So that's like this bottom section here is basically like a cross product-y thing to map the torque into those guys. And the rest of this is very standard stuff. F equals MA stuff. Stance dynamics, basically the only difference here is I've zeroed out all the stuff for the foot and it's only affecting the body now. RK4 for everything. And then here's my jump map. I'm just zeroing out the velocities, both vertical and horizontal for the foot. This is, exactly the stuff we wrote down. Cost weights, these are just totally made up. It's like identity stuff for the Q's and R's, quadratic costs like we're used to doing. Here's where we'll talk about this a little bit. It's an LQR style quadratic cost, but I'm having a reference trajectory in here for the X's and U's. So I'm actually writing down like some kind of like reference tracking style quadratic cost. We'll talk about what the reference is in a second, but that's important, it turns out, to get this to work. This is sort of the voodoo-y, art of doing this stuff. So here's this reference trajectory. So I want to make it hop. Right now, the first thing we're going to do is make it hop in place. So to get it to hop in place, what I'm going to do is just write down a sinusoidal reference trajectory that I'm going to apply to like the z-axis positions of everything. So that's that. Here's what it looks like. And this is going to go in the cost function as the reference that it's going to try to track. So what this kind of lets me do is draw a cartoon of like the motion of this thing. And then what the trajop solver is going to do is try to track that cartoon motion that I just wrote down while actually respecting the dynamics, right? So it's going to do like the best job it can to track this stupid cartoon trajectory with the real physics. Dynamics constraints. Okay, so this is looping through doing the thing we just talked about. So looping through stance phase dynamics, flight phase dynamics, jump map, stance phase dynamics, flight phase dynamics, blah, 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 jump map, right? Like we said, applying them to groups of 5 knot points, 5 knot points. Stance constraint, this is saying it actually has to be in contact with the ground when it's in stance phase. Length constraint, that's the prismatic joint length constraints we put in there. This is just stacking up all the constraints. And then this is, all this is just interfacing to IP-opt. So it's ugly and it's a lot of boilerplate code, but there's nothing interesting or deep there. It's just crap to call the solver. So there's that. Yeah, nothing worth talking about there, I don't think. Random, I'm putting in like a dumb random initial guess. And then I'm going to call a solver. And this is kind of slow because I've been really naive and dumb about how I set the problem up and not done any smart sparse matrix stuff, which you guys should do on your homework for extra points. Okay, so yeah, I don't know, it took like 20 seconds to solve. Optimal solution found, hooray. So now we can plot this stuff. This is the body height and this is the foot height. So you can see the foot's, stance face, flight face, blah, blah, blah. This is basically zeros, 20 minus 7, that's just noise. And let's go animate this thing. None of this is interesting. Okay, here we go, visualizer. Yeah, hopping up and down. That's kind of cute. Okay, so now, so we can make it hop up and down. Let's now make it actually move and hop somewhere. So to do that, what I'm going to do is go back to this reference trajectory thing. And instead of just hopping straight up and down, so this is the Z coordinate, right? Sinusoid. I'm going to now add a linear reference to the X coordinate, just like linear interpolation, right? From like -1 to 1. And what is this? Oh yeah, same thing for the foot. Linear interpolation on the foot. And then putting in like, linear velocities that are consistent with that linear interpolation on the position. So we're going to make that the reference now and try to track that instead. And I guess I'll just kind of go through all this crap. Yeah, we'll solve that. And by that whole like reference tracking costing, that's like kind of the art of doing this stuff. I mean, I've done this a lot, so I know how to get this to work kind of like, within the first couple of tries, but that's definitely like when you get into this stuff, being able to like set up cost functions is sort of an art form and you kind of just have to get good at it. Okay, so this is like, the X position showing it's moving sideways. Let's just go watch the animation. So cool. Can move to the right. That's kind of fun. And yeah, it's pretty easy to go nuts with this. Like you can make this do, with some pretty basic ingredients. Now I can make this do whatever I want by just going in there and drawing cartoon reference trajectories. I saw actually a conference I was just at last week. This lab from UW, Bechet Achikmase, who's awesome optimal control guy. They made a tablet interface to their TradJop solver, so you could draw reference trajectories on the tablet and like put in obstacles, and then it would like automatically solve and fly the quad rotor through. I thought that was super slick. It's like, people in my lab, like you get good at like doing this reference trajectory stuff and like writing code to do this stuff, but like, all I'm doing here is really dumb stuff, right? I'm like drawing cartoons basically, and then asking the solver to make the robot follow the cartoon. And you can imagine easily doing this with like a tablet interface with your finger or something. It'd be super fun. So I've like always wanted to do that. And this other lab kind of did it for quad rotors, but you can imagine doing it for all kinds of things. Anyway, so yeah, and you can kind of go nuts with this. This is literally this set of ideas, and this basic setup is pretty much how Boston Dynamics makes the Atlas do insane parkour moves and stuff. Yeah, okay. Anyone want me to try anything? Yeah.
If you didn't have the sinusoidal y and you just had a straight line, would it still be able to follow it?
It would probably not converge to anything smart. I mean, we can try it. What do you want to do? You want to put like linear interpolation on the height or something? You want to set the height constant? My guess is that it would not figure out how to hop.
Okay.
And it would just sit there and like try to slide sideways and not do anything good and barf at you. So we can try it though. So you want me to set this? Should we set? So we want to just set this to ones basically.
Yeah. Or some kind of
Yeah.
You want to set it to like 2, so it's higher.
This is the head.
Right.
When we
So
said
it
it's,
can go up to 1.5,
you can go between 0.5 and 1.5. This is just a reference that I'm putting in a quadratic cost though. This is not a constraint or anything, right? It's just saying like, be there-ish, right? But I'm pretty sure if I do this, it's just gonna, I think it's just gonna sit there and try to slide sideways, which it can't do, and then not do anything.
Because of like the optimization vector, we use the local minimum in order to be able to find the trajectory.
Yeah, so this is, again, it goes back to the fact that this is all local optimization. And essentially, with all these methods, you're gonna go downhill into the in the nearest basin of attraction kind of thing. And by, so the initial guesses matter a lot in this kind of stuff, right? So here, so that's the reference now for the body position. I'm guessing the solver is just going to barf and sit there and not do anything. That's probably what's going to happen. But yeah, like it's usually not hard to come up with reasonable initial guesses though. Like this kind of stuff it takes like a little bit of intuition for the problem. What did it do? Optimal, well, let's see what it did. I have no idea what it's going to spit out. It did figure out how to hop. Was there something else in there? There might have been some, I might not have actually. Yeah, no, this is too sketchy. I don't think that actually did what I wanted. No, this is just spitting back what we had before. I probably messed up. Where did this go? Reference. I almost certainly messed this up, or it's somehow warm starting without me telling it to or understanding what's going on. Anyway, but yeah, I'll post the code. You can go nuts and try a lot of things. You can definitely like make cool things happen with this stuff.
You make the floor not sticky.
So let it slip.
Yeah, like change the.
So not easily with this setup, because we're doing this hybrid thing, right? And what I would have to do to make that happen is actually introduce a new mode to the hybrid thing with a sliding mode and like extra constraints and extra jump maps for stick slip and this kind of stuff. So you could do it, absolutely, but it's a lot more work and a lot more code to write. So we're not gonna do it. Yeah, sorry, I don't know. I might have to like, there's probably some kind of global variable thing in here that's messing me up. Yeah.
So, say, this is like, Boston Dynamics like a spot.
Yeah.
And like, you're doing like, just locomotion. But if you wanted to use something like this, like, it's similar to the question, like, how do you handle like all the different like modes of slip that you can have?
Yeah, so you kind of don't at this level. So remember, this is basically planning. This is like offline generating like a template motion kind of thing. Online, you have some kind of feedback controller that's trying to track this on the real robot. And that's kind of generally treated as a separate thing. Usually, practically on most of these robots right now, people are doing MPC. And so usually you'd have something like this, and then you'd track it with one of these like QP-based MPC controllers. And in that controller, you'd have a bunch of stuff to handle, disturbance rejection, like if the foot slips, push recovery. There's a lot of stuff like that in these online feedback controllers. So that's kind of, does that answer your question?
Yeah. So I guess like this handles a higher level. And then I had a similar question related to that. So like, you have like a reference trajectory that is more precise, like does that make the problem harder to solve or having some more?
What do you mean by more precise?
Like I'm thinking here we just have like some sort of like sine wave to represent the gates. That sounds pretty easy to control. So you have like something that's just like a very precise motions kind of specific like links or something. I don't know. I'm just thinking like is this like you run into the case where it's over constrained?
Yeah, I mean, you definitely can. So here, like what I'm doing here, right? That like reference thing is it's in the cost function. So it's not a hard constraint. So I'm not actually exactly following it. This is what I'm writing down in this problem is basically like, here's this random sinusoidal thing I just cartooned out. Try to track that while obeying all the physics constraints, right? So it's not exactly following that. It's gonna like do the best it can, whatever, and not really worry about it too much. If you made those things hard constraints instead of soft cost things, then you can definitely get into situations where you get infeasible problems where it can't satisfy the constraints. So yeah, it's often like the difference between a constraint and a cost and like where to put things is part of the art of doing this, I would say. And generally speaking, what you want to do is encode behavior in the cost function and encode physics in the constraints. That makes sense. I don't know. Yeah. Anybody else? You want to try anything else? No? All right. In that case, I think we're pretty much done for today. I'll write some like little summary notes, I guess, on this stuff. But yeah. Yeah.
So, for the guard function, it seems like it's very environment related. Like, if it's not flat.
Oh, yeah.
surface, Then it will you have to block?
Yep. So yeah, doing this on like rough terrain and stuff like that can get very messy. Generally speaking, like what most of the current stuff does is, so either like the Boston Dynamics demos you see, they're in a lab, so they know exactly where everything is and they can characterize it perfectly. Some of the more impressive, like robust locomotion things you've seen from like the MIT Cheetah, kind of people and stuff like this, like what they're basically doing is assuming the ground is flat, and then anything else is a disturbance as far as the controller is concerned. So they're not doing a lot of there's no vision typically in these control loops. Sometimes there's like foot pressure sensors in there in various ways. Usually it's just proprioception. It's just like measuring joint angles and motor torques and stuff like this to figure out if you're in contact or not. And yeah, usually it's surprising, but yeah, those QP based MPC controllers, I kind of like said a lot, about this earlier, but they work incredibly well and they're really robust. And like basically all the walking robot stuff you see right today is all doing some form of QP based MPC with like linearized dynamics and stuff. And it works really, really well. It's like surprisingly robust. So yeah, pretty much what they're all doing. They might have a couple of canned gates in there for like flat ground. And sometimes they'll have another canned gate for like stairs. And anything else, like as far as like terrain variation stuff is all just kind of treated as a disturbance. And then you design a like pretty robust controller that can handle large disturbances and you're pretty much good to go. Anybody else? Yeah.
Can you make it do like a backflip? Do you have like a reference here?
Oh yeah, for sure. Yeah, we can make this do a backflip. I just have to sit here and play around with the cost function a bunch. But yeah, you can definitely do a backflip. Bonus points if you take this code and make it do a backflip. You definitely can do it. Yeah, it's actually not even that hard on this one. It's pretty easy. You would basically give it a reference where the angle goes around like 2 pi and like set up the stance and flight phase stuff appropriately with the constraints and hit go, and it would definitely work. Yeah, that one's not too bad actually.
Will only constrain the body, not the foot. You just get around the weight, the cost of the foot, and so is the reference structure of the body.
That's actually kind of what I'm doing here. I think like, so the hopping reference, I was actually only giving that sinusoidal reference on the body. And it just figures it out. It's like, it doesn't have to be very good, right? It's kind of like a very cartoony thing that sort of gets it in the ballpark, right? And then the solver can kind of dial it in all the way. All right. Cool. All right, guys. Yeah, that's kind of it.